We generally expect the next era-defining breakthroughs to emerge from Silicon Valley. We look for progress in artificial intelligence, microscopic semiconductors, or the high-density batteries powering electric vehicles. Yet one of the most significant developments in power generation is currently operating here, on the foundry floor of a heavy industry steel plant in China. Hidden among this heavy machinery is a remarkably tiny device. Despite its size, this system is challenging a 140-year-old standard of how humanity produces electricity. This machine is 50% smaller than its predecessors, yet it generates 50% more electricity without using a single drop of water. Its success forces us to ask why we still rely on a power generation model that predates the first airplane. To keep the modern grid running, we invest billions into sophisticated fuels. We split atoms in nuclear reactors and capture sunlight in vast thermal arrays. But looking past the uranium and mirrors, the underlying mechanical reality is surprisingly simple. These facilities are ultimately high-tech ways to heat up water. The process follows a 19th century blueprint. The fuel generates heat, the heat boils water, the water creates steam, and that steam physically turns a turbine. Even in a digital world of servers and smartphones, the physics powering our homes remain locked in the era of the steam locomotive. The primary bottleneck in modern energy isn't a lack of better fuel, it is our reliance on steam as the vehicle to move that energy. The global power grid is currently facing a massive failure in energy retention. A standard steam-powered turbine only reaches an efficiency rate of about 35%. This means the majority of the heat generated by our fuel is entirely lost during the conversion process. You can see that energy escaping into the atmosphere as thick plumes of white vapor rising from concrete cooling towers. This is the Carnot limit, a strict thermodynamic boundary that defines the maximum possible efficiency of any heat engine using steam. Engineers are trapped by physical constraints. Increasing the steam temperature eventually melts the turbine blades, while increasing the pressure makes it too expensive to manufacture. Steam technology hasn't failed. Rather, it has been optimized to its absolute maximum physical limits. To make a significant leap in energy capture, we have to change the fluid in the pipes. This leads to a critical question. What if, for the last century, we've been trying to optimize the wrong part of the system? Instead of trying to build a stronger turbine, researchers decided to replace water entirely as the working fluid. They chose carbon dioxide and actively pressurized it into a very specific, highly unnatural physical state of matter. By discarding water, engineers bypassed the 140-year-old thermodynamic wall, transforming CO2 into an incredibly efficient medium for energy transmission. This is known as the supercritical state, a hybrid phase of matter where the CO2 is no longer entirely a gas, but not quite a liquid either. Compared to steam, which is light and bulky, supercritical CO2 is incredibly dense. Because it is as dense as a liquid, it can drive a drastically smaller turbine while extracting the same amount of kinetic energy. Because it still flows effortlessly like a gas, it moves through the system with less friction, allowing for vastly superior heat reuse. These properties result in a massive mathematical jump. Theoretical energy efficiency climbs from the 35% average of steam to nearly 50%. This supercritical fluid essentially hacks the laws of thermodynamics, capturing a significant portion of the energy that we once accepted as permanent waste. Inside this Chinese steel mill, the technology is already operational, actively recovering extreme waste heat from the foundry floor. If heavy industries globally swap standard steam turbines for supercritical CO2 systems, industrial energy consumption and emissions would be completely rewritten. If the efficiency gains are this significant, the question is why the technology remained restricted to theoretical models for so long. The delay reveals the gap between a revolutionary idea and the material science required to actually build it. Engineers identified supercritical CO2 as a high-efficiency solution 60 years ago. For decades, however, every attempt to move beyond the laboratory hit a wall of physics. The system requires extreme operating temperatures. In traditional metals, these temperatures cause carbonization and physical creep, leading to the rapid degradation of internal components. Further complications arise within the heat exchangers. These components must manage immense, supercritical pressures while maintaining structural integrity across these dense, honeycomb-like microstructures. The turbine itself must spin at ultra-high speeds, requiring magnetic bearings that can withstand extreme duress. In this environment, a single component failure results in the total destruction of the unit. This 60-year gap in development reflects a lack of capable materials. The technology could only transition to the real world once humanity developed metals and bearings that could survive the violent conditions of the process. The first commercial breakthrough is currently happening on the floor of a working Chinese steel mill. This unit, the Chaitan-1, functions by capturing the waste heat naturally exhausted during steel production. It weaponizes that thermal energy, converting it into power rather than allowing it to vent into the atmosphere. This recycling process generates approximately 70 million kilowatt-hours per year. This is energy recovered entirely from an existing industrial process. Maintaining stable operations in a loud, high-demand industrial environment marks the end of the invention phase. It signifies the start of commercial viability. A traditional steel plant serves as a strategic proving ground for this technology. The mill provides a constant, high-hour operating environment. This allows engineers to rack up thousands of hours of runtime with relatively low risk to the broader energy grid. This dashboard tracks the metrics that determine the technology's future. Every hour of operation yields precise data on durability, corrosion resistance, and total maintenance cost. In the energy sector, this accumulation of performance history provides the empirical proof required to justify a massive capital investment. Shifts in heavy industry are not won through announcements. They are won through the relentless, documented accumulation of operational hours. Technological transitions follow a predictable cycle, moving from invention to proof, through data collection and economic validation, and finally to total replacement. The original steam turbine spent decades in this cycle before achieving its global status. The supercritical CO2 turbine may be at a similar pivot point as the mobile industry was in 2007, a moment where the hardware finally aligns with the long-term vision of the field. However, it remains to be seen if this technology will successfully dethrone the steam-based status quo or remain a niche engineering curiosity. The outcome depends on whether the data currently emerging from this single steel mill can scale into a broader economic advantage. A transition of this scale will take time. Legacy steam power is an entrenched global system that will likely persist for several more decades. History suggests that major transitions often begin with a single machine operating in an overlooked location. We traditionally look to established innovation hubs like Silicon Valley for shifts in global infrastructure, yet the data for this energy transition is being generated inside a gritty industrial facility in China. While the steam age is not over, its replacement is currently being tested in the real world. Let me know your perspective in the comments. How would the world change